question A, solve z squared is -1 minus the square root of 3i, given your answer in the modulus argument form. It is not specified that theta, the argument must be in radians. I will use degrees. How to solve z to the power of n is equal to some complex number. First of all, this complex number should be rewritten in the Euler's form. It's actually the modulus argument form. The modulus multiplied by e to the power I multiplied by the argument theta, and then roots are zk. This modulus to the power 1 over n multiplied by e to the power I theta k, where theta k is given argument divided by n, plus 2 pi k when it is measured in radians, or 360 k when it is measured in degrees. The argument is measured in degrees over n for k is 0, 1 up to n minus 1, so that there are n roots and solutions in total. So let's rewrite this in the Euler's form. We need the modulus and argument. The modulus is square root of x squared plus y squared when a complex number is given as x plus y I, or if you illustrate it on the organ the diagram, it's just distance from the origin and from the right angle triangle. It's just the Pythagoras theorem, real, imaginary, -1, negative root of 3i, so it's somewhere here, and you can see that it's a required modulus, and you can see that it's a square root of 1 squared plus root of 3 squared, and it's 2. And the argument, it's the angle from this point is 0, and in anti-clockwise there are positive angles, in clockwise there are negative angles, and we need this angle. It's the required argument, and we consider this small right angled triangle, and this small angle, tangent of this angle, it's what, root of 3 over 1, and tangent is sine over cosine, and the sine to be root of 3 over 2, it's 60. Sine is root 3 over 2, cosine a half, so finally it's root of 3. So it's 60, and finally the argument is 180 plus 60 is 240. Or without the organ diagram, you may use just a formula for the modulus is square root of x squared plus y squared, and for argument it's just arctangent of y over x for the first and the fourth quadrants, and the pi of 180 plus arctangent of y over x for the second and the third quadrants. And notice that arctangent is odd function. Arctangent of negative value, it's negative arctangent, so for this problem it becomes pi of 180 plus 180 plus arctangent, and the complex number is -1 minus root of 3i, so it's negative root of 3 over -1, so it's just root of 3, it's plus, so it becomes 180 plus 60. For the second quadrant it is negative, and it becomes pi minus arctangent of a positive angle. So z squared is 2 e to the power of 240 degrees I. Then roots are zk is square root of 2 e to the power of I theta k, where theta k is 240 degrees over 2 plus 360 degrees k over 2. We can simplify and it becomes 120 plus 180 k, for k is 0, 1. If you consider k to be 2, you get this complex number, but argument will be rotated by one revolution, so it's plus 360, and if you rewrite in the Cartesian form x plus iy, you get absolutely equivalent complex number, so it's actually the same. So for angles from 0, for arguments from 0 to 360, there are two solutions. So Z0 is, it doesn't matter, you may use Z1, Z2, just the k is 0, so I use also Z0 is square root of 2 e to the power of I, when k is 0, it's 120 degrees I, which is square root of 2 times cosine of 120 plus I sine of 120. It's in the modulus argument form, and we need in this form. And the next, Z1 is square root of 2 e to the power of, when k is 1, it's 300 degrees I, which is square root of 2 times cosine of 300 plus I sine of 300 degrees. You may add or subtract any number of full revolutions, 360 or 2 pi. So in general, you may rewrite it if it's required that it's cosine of negative 60 and it's sine of negative 60, and remember that cosine is even function, so it's the same as cosine of 60, and sine is odd function, so it's the same as minus sine of plus 60. So it can be rewritten as square root of 2 cosine of negative 60 plus I sine of negative 60. It's the same. The next, let Z1 and Z2 be the square roots of the same complex number, negative 1 minus square root of 3i. And let Z3, Z4 be the square roots of negative 1 plus root 3 plus I. You can see that it's the same but complex conjugate. Complex conjugate, it means that every I becomes negative I. Question B, expressing your answer in the form a plus bi, find Z1 and Z2 and deduce Z3 and Z4. So when Z is square root of this, it's the same as we solve Z squared is negative 1 minus root of 3i, so it's absolutely the same. So Z squared is this, it's the same as Z is square root of this. And we need that the real part of Z1 be positive, and we need in the Cartesian form, so we continue actually this, and we need to calculate the values of cosines and sines, and this value, or this complex number, cosine of 300 and sine of 300, so 300 is the fourth quadrant, so this complex number is in the fourth quadrant, so cosine is positive, sine is negative, and cosine is the real part, so for this complex number the real part is positive, so it is our Z1. So Z1 is this complex number, square root of cosine of 300, and cosine of 300 is cosine of negative 60 degrees, cosine of negative 60 is the same as cosine of plus 60, and it's a half. and sine of 300 is sine of negative 60, it's minus sine of 60, and it's root 3 over 2i, and finally it's root of 2 over 2 minus root of 6 over 2i. The real part is positive as required. And another solution, cosine of, it's z2, it's root of 2, cosine of 120, it's cosine of 180 minus 60, and it's negative cosine of 60, it's negative a half, and sine of 120, it's sine of 180 minus 60, and it's the same as sine of 60, so it's plus root of 3 over 2i, so it's negative root of 2 over 2 plus root of 6 over 2i. The next, deduce Z3 and Z4, and it's Z3 and Z4 are the square roots of the complex conjugate. I just remember that Z complex conjugate squared is equal to Z squared complex conjugate, and applying to our roots Z1, Z2, it becomes that Z1, Z2 squared is what, negative 1 minus root of 3i, and then complex conjugate is equal to Z1, 2 complex conjugate squared, and complex conjugate is negative 1 plus root 3i, and then applying square roots on both sides, it becomes that the square root of negative 1 plus root 3 over I is just that 1, 2 complex conjugate. So you should deduce that solutions are just complex conjugates. And the real part of Z3 is positive, so Z3 is this root 2 over 2 plus root 6 over 2i, and Z4 is negative root 2 over 2 minus root 6 over 2i. The next, the four roots are represented by the points A, B, C, D respectively on the organ diagram. Plot the points and find the area of polygon formed. The real part, the imaginary part, and Z1 plus minus somewhere here, so it's Z1, so it's root 2 over 2, and it's negative root 6 over 2, negative root 2 over 2, minus plus somewhere here it's Z2, and Z3 plus plus, and Z4 minus minus somewhere here, so that we get a rectangle. Definitely there must be same distances. Something like this. And the area of this polygon is, there are 4 such small rectangles, and for each it's width times length. So area, question C, area is 4 times root 2 over 2 times root 6 over 2. So it's root of 12 or 2 times root of 3. The next, the 4 roots, the same roots, satisfies the equation z to the power 4 plus 2 z squared plus 4 is 0. The 4 roots 1 over z1 and so on satisfies the equation given. Find the value of p, q, and r. Since 1 over z is a root solution, we can substitute it for w to get that it becomes p 1 over z to the power of 4 plus q 1 over z squared plus r is 0, and common denominator is z to the power of 4, and it becomes p plus q z squared plus r z to the power of 4 is 0, and fraction is equal to 0 when numerator is 0, so r z to the power of 4 plus q z squared plus p is 0. But it's the same z, and just we compare with this to conclude that r is 1, q is 2, and p is 4. The next, the 4 roots 1 over z1 and so on are represented by the points respectively on an organ diagram. Find 1 over z in the form, the Cartesian form. What is z1? It's root of 2 over 2 minus root of 6 over 2i, and common denominator is 2, and let's factor out root of 2, so it becomes 1 minus root of 3i, and we need 1 over z1, it becomes 2 over root of 2, or just root of 2 in the numerator, and 1 minus root of 3i in the denominator. And multiplying numerator and denominator by complex conjugate by 1 plus root of 3i, we get that it becomes a formula a minus b times a plus b, so that it's a squared minus b squared, so that I disappears. So it's 1 squared minus root of 3i squared. It's I squared, it's negative 1, so it's 1 plus 3, so it's 4. And in the numerator it becomes root of 2 plus root of 6i, and it becomes root of 2 over 4 plus root of 6 over 4i. and hence deduce the area of the polygon formed by these 4 points. You can see that it was like this, 4 points, and now we consider this point, root of 2 over 2, and negative minus root of 6 over 2, and it becomes root of 2 over 4 and root of 6 over 4. So each coordinate decreases by factor of 2, the real part and the imaginary part. So that we can suggest that each coordinate decreases by a factor of 2, and hence area decreases by factor of 2 squared by a factor of 4. It becomes over 4 over 4 over 4 over 4, and the same but over 4 over 4, so it becomes 2 over 2 times root of 3 divided by 4, not by 2, because for this small triangle this decreases by factor of 2, and it also decreases by factor of 2, so that the area decreases by factor of 4, which is root 3 over 2. And that's all for this question.